Phasor diagrams illustrate the relationship between voltages and currents in alternating current circuits, providing a visual representation of their magnitudes and phase angles. When dealing with two 150 kV amps delta/Y transformers in parallel, understanding Phasor diagrams becomes crucial for analyzing their behavior, especially under matching and mismatched impedance conditions. Firstly, let's consider the scenario where the transformers have matching impedances. In this ideal situation, the primary line currents of both transformers will be equal, and consequently the secondary line currents will ideally be zero. The Phasor diagram in this case will depict the primary line currents and voltages as being in phase with each other. This indicates that both transformers are sharing the load equally and operating efficiently without any circulating currents between them. Now, let's examine the more realistic scenario where the transformers have mismatched impedances. In this case, the primary line currents will no longer be equal, and the secondary line currents will be non-zero. The Phasor diagram will show the primary line currents and voltages as being out of phase. This phase difference arises because the transformers are not sharing the load equally due to their differing impedances. The circulating current is essentially the difference between the primary line currents. This circulating current flows between the transformers, leading to increased losses and potentially overloading one of the transformers if not properly managed. To effectively size wires and select appropriate breaker protection for these parallel transformers, it's essential to consider the maximum current that each component will experience under both matching and mismatched impedance conditions. For primary wires, these should be sized based on the primary line current, denoted as I only. A wire with an adequate ampacity rating to handle the maximum expected current flow is necessary to prevent overheating and potential fire hazards. Similarly, the secondary wires should be sized based on the secondary line current, denoted as ISON. The selected wire must be rated for the maximum secondary current to ensure safe and reliable operation. For breaker protection, a circuit breaker needs to be selected that is rated for the maximum primary line current, IONI. The circuit breaker's purpose is to protect the transformers and connected equipment from overcurrent conditions such as short circuits or overloads. By selecting a breaker with an appropriate current rating, the system can be automatically disconnected in the event of a fault, preventing damage and ensuring safety. To illustrate these concepts, let's consider a practical example involving two 150 kV amps, 4160/2400 volts, delta/Y transformers. Suppose that the impedances of these transformers are as follows. Transformer 1 has an impedance only equal to 0.2 plus J 0.15 ohms per phase, while Transformer 2 has an impedance C2 equal to 0.3 plus J 0.20 ohms per phase. Firstly, we can calculate the primary line current under matching impedance conditions. Assuming that the transformers are perfectly matched, the total impedance would be the sum of the individual impedances. The primary line current, IONI, can be calculated by dividing the primary line to line voltage, which is 4160 volts, by the total impedance, which is the sum of zone and Z2. Therefore, IONI equals 4160 volts divided by the sum of 0.2 plus J 0.15 ohms and 0.3 plus J 0.20 ohms. This calculation yields a primary line current of approximately 16.35 amps. Next, let's calculate the primary line current under mismatched impedance conditions. In this case, each transformer's current must be calculated separately. The primary line current for Transformer 1, IONI, is calculated by dividing the primary line to line voltage, 4160 volts, by its impedance, zone, which is 0.2 plus J 0.15 ohms. This results in a primary line current of approximately 16.63 amps. Similarly, the primary line current for Transformer 2, ITWO, is calculated by dividing the primary line to line voltage, 4160 volts, by its impedance, C2, which is 0.3 plus J 0.20 ohms. This results in a primary line current of approximately 16.4 amps. The circulating current is then the difference between IR and IR, which is 16.63 amps minus 16.4 amps, resulting in a circulating current of approximately 0.59 amps. Now let's calculate the secondary line current under both matching and mismatched impedance conditions. Under matching impedance conditions, the secondary line current, ISON, can be calculated using the formula ISON equals IONI multiplied by Z2 divided by ZS, where ZS is the secondary impedance. Assuming a secondary impedance of 0.1 plus J 0.5 ohms, the secondary line current is 16.35 amps multiplied by 0.3 plus J 0.20 ohms divided by 0.1 plus J 0.5 ohms, resulting in a secondary line current of approximately 8.18 amps. Under mismatched impedance conditions, the secondary line current, ISON, can be calculated using the formula ISON equals IONI multiplied by ZS divided by Z2. Using the same values as before, the secondary line current is 16.63 amps multiplied by 0.1 plus J 0.5 ohms divided by 0.3 plus J 0.20 ohms, resulting in a secondary line current of approximately 8.31 amps. Based on these calculations, we can determine appropriate wire sizes and breaker protection for the transformers. For the primary wires, a wire gauge that can handle the maximum primary line current is needed. In this example, with a primary line current of approximately 16.63 amps, an American wire gauge number 8 wire, which is rated for 40 amps, would be suitable. For the secondary wires, a wire gauge that can handle the maximum secondary line current is needed. In this example, with a secondary line current of approximately 8.31 amps, an American wire gauge number 4 wire, which is rated for 70 amps, would be appropriate. For breaker protection, a circuit breaker that is rated for the maximum primary line current is needed. In this example, with a primary line current of approximately 16.63 amps, a 20 amp circuit breaker would provide adequate protection. In summary, understanding Phasor diagrams is essential for analyzing the behavior of parallel transformers, especially under matching and mismatched impedance conditions. By calculating the primary and secondary line currents and considering the maximum current that each component will experience, appropriate wire sizes and breaker protection can be selected to ensure safe and reliable operation. Additionally, it's important to note that the impedance values used in these calculations are simplified representations of the actual transformer impedances. In practice, transformer impedances can be more complex and may vary with load and operating conditions. Therefore, it's recommended to consult with a qualified electrical engineer to perform a thorough analysis of the transformer system and determine the appropriate wire sizes and breaker protection. Furthermore, it's important to comply with all applicable electrical codes and standards when installing and operating parallel transformers. These codes and standards provide guidance on safe wiring practices, overcurrent protection, and other safety measures that are necessary to ensure the safe and reliable operation of the electrical system. In addition to the wire sizing and breaker protection considerations, it's also important to consider the voltage drop in the primary and secondary circuits. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the impedance of the wires. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. To minimize voltage drop, it's important to use wires that are large enough to carry the current without excessive voltage drop. The voltage drop can be calculated using the following formula: voltage drop equals current multiplied by impedance. The impedance of the wires can be calculated using the following formula: impedance equals resistance multiplied by length. The resistance of the wires can be found in electrical codes and standards. In addition to the voltage drop, it's also important to consider the harmonic content of the current. Harmonics are sinusoidal waveforms that are multiples of the fundamental frequency. Harmonics can be generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause a number of problems, including overheating of equipment, increased losses, and interference with other electrical equipment. To mitigate the effects of harmonics, it's important to use harmonic filters. Harmonic filters are devices that are designed to reduce the harmonic content of the current. Harmonic filters can be installed at the load or at the source. When installing parallel transformers, it's important to ensure that the transformers are properly phased. Phasing refers to the alignment of the voltage waveforms of the transformers. If the transformers are not properly phased, it can result in circulating currents and other problems. Phasing can be checked using a phase meter. A phase meter is a device that measures the phase angle between two voltage waveforms. When installing parallel transformers, it's also important to ensure that the transformers are properly grounded. Grounding refers to the connection of the transformer neutral to the earth. Grounding provides a path for fault currents to flow to the earth, which helps to protect equipment and personnel from electrical shock. Grounding should comply with all applicable electrical codes and standards. Finally, it's important to perform regular maintenance on parallel transformers. Maintenance includes inspecting the transformers for damage, cleaning the transformers, and testing the transformers. Regular maintenance can help to prevent problems and ensure that the transformers are operating safely and reliably. In summary, installing and operating parallel transformers requires careful planning and consideration. By following the guidelines outlined in this discussion, you can ensure that the transformers are operating safely and reliably. Remember to consult with a qualified electrical engineer to perform a thorough analysis of the transformer system and determine the appropriate wire sizes, breaker protection, and other safety measures. This will ensure the safe and efficient operation of your parallel transformer system.